Okay, welcome to our review of radicals. Guys, it's absolutely imperative you understand the rules of radicals and how radicals work as far as being simplified, multiplying, dividing, adding, subtracting, everything, because we will be working with radicals literally the rest of the year. The sooner you understand them, the better off you are. On this first slide, these perfect squares are huge. You should know what perfect squares are. They are basically numbers that when square rooted will give you a whole number, an integer, a positive integer as an answer. In other words, the square root of 1 equals 1. That's why 1's a perfect square. The square root of 4, if I can write that down, the square root of 4 equals 2. That is why 4 is a perfect square, etc., etc. All the way up. I only gave you the first 15. The square root of 225 is 15. Most commonly used are 121, 144. We don't see 169, 196, 225 a whole lot, but you should know up to 225. Those are all perfect squares. Now, excuse me, the other perfect squares that are important for us would be variables raised to even powers. The square root of x squared is going to be x. And basically, as a rule of thumb, if you square root any variable raised to an even power, you're just going to cut the variable in half. So the square root of x to the 4th is x squared. The square root of x to the 20th is x to the 10th. Why? Because x to the 10th times x to the 10th is x to the 20th. If you remember your rules of exponents, you add exponents. So x to the 10th times x to the 10th is x to the 20th. So, the next several slides, there's actually 15 slides here, all have to do with radicals. You can watch this video as many times as you want. Pick and choose which examples you want to see over and over again, because I promise you, one of the hardest concepts for guys second semester geometry is radicals. The first thing we're going to talk about is simplifying radicals. If one of those perfect squares that we just talked about, the 1, 4, 9, 16, etc., if one of those perfect squares is a factor of the number that we are simplifying, our radical is not simplified. For an example, 8 is 4 times 2, so the square root of 8 is root 4 times root 2. So the reason the square root of 8 is not simplified is because its factors 4 and 2, one of them is a perfect square. And I know that the square root of 4 is 2. And one of the things that I tell guys that's super important in this chapter and with radicals, when you are simplifying, and I'm going to write this again above, do not call radical 8 4 times 2. It is not 4 times 2. This leads to plenty of mistakes. You have to be organized. 4 times 2 is 8. Going back below here, root 4 times root 2 is root 8. And I know the square root of 4 is 2, so what I do at the end is I circle my numbers that can no longer be simplified. 2 is 2. I can't simplify it. Square root of 2, that is also simplified because there are no perfect squares other than 1 that are factors of 2. So what I do at the end is I take the two numbers that I have circled and I multiply them together. The multiplication sign is assumed, not seen. 2 root 2 is my answer. That means 2 times the square root of 2. Now when we have bigger numbers, like the square root of 250, again, I want to pick perfect squares that are factors of 250. And the first one that comes to my mind is 25 times 10, because 25 is a perfect square. Now, hopefully you noticed what I just did, I never want to see. Do not write 25 times 10. That is not true. 25 times 10 is 250. Root 25 times root 10 is root 250. So the square root of 25 is, of course, 5. I'm done with it. I no longer have a square root around the 5 because the square root of 25 is a whole number. It's a positive integer, 5. Square root of 10 has no perfect squares that go into it, so I'm going to leave it alone, and my final answer is 5 root 10. Go ahead, if you don't believe this, take a calculator, punch in the square root of 8 and see what decimal it gives you. And then take the same calculator and multiply 2 times root 2, and you'll see you'll get the exact same answer. It's the same number. Same thing, take the square root of 250, see what that gives you as a decimal, and then check to see if it's the same as 5 root 10. It for sure will be. I'm going to continue simplifying radicals here. Now notice, I have the same problem twice, and there's a reason for that. When I'm simplifying radicals, my goal is to find the biggest perfect square that goes into my number 32. Now, sometimes it's easy to see, and sometimes, it's not so easy. For me, it's easy to see that 32 is 16 times 2, so the square root of 32 is root 16 times root 2. The square root of 16 is 4, circle, circle, and my final answer is 4 root 2. Now, let's just say, okay, I did not come up with the largest perfect square of 16, and I called the square root of 32 root 8 times root 4. Still a pretty good option because the square root of 4 is a perfect square. The square root of 4 is 2. Do not leave your answers to radical 8. That's not correct because root 8 can be broken down into root 4 times root 2, and the square root of 4 is 2. This is where organization is really, really important. You have 3 numbers circled because they can no longer be broken down. What do I do with these 3 numbers? I take them and I multiply them together. 2 times 2 is 4, so my final answer is 4 root 2, which of course matches up to my 4 root 2 that I got in the first time I did this problem. So, the point here is that sometimes the same answer can be found by using different factors of the same number. Square root of 162, next example. This is a little bit bigger number. So if you think about it, you think, well, what perfect squares can go into 162? Well, it just so happens that the square root of 81 times the square root of 2 is equal to 162, square root of 162 I should say, and the square root of 81 is 9. So I'm going to circle those 2, and my final answer, simplified, is 9 root 2. Another rule when we deal with radicals tells us that we can never have radicals in the denominator. So in this particular slide, you can see I have the same problem twice. It's because we can do this problem multiple ways. The first way we can do this is by simplifying root 8 right out of the gates. The square root of 8 is root 4 times root 2, and the square root of 4 is 2, so we can call the square root of 8 2 root 2. So I could rewrite this problem as 6 over 2 root 2, and then 6 over 2 is 3, so we can call this 3 over root 2. Now, this answer is still not simplified because, like I said, we cannot have a radical in the denominator. So it's really simple what we need to do. It is legal in mathematics to multiply any number in the world by 1, and we will come up with exactly what we started with. So what I'm going to do is multiply by 1. However, I'm going to do it in a fancy way. Radical 2 over radical 2 is 1. Root 2 divided by root 2 is 1. However, what you'll see, when I multiply in the numerator, I get 3 root 2. When I multiply in the denominator, root 2 times root 2 is 2. Now, some guys will say, well, wait a minute, isn't root 2 4? Yes, it is, but the square root of 4 is 2, like I have in the denominator, so that is my final answer, 3 root 2 over 2. Odd-looking answer, but the correct answer. The second method we could use here, I could flat out, right out of the gates, multiply by root 8 over root 8. What that'll give me is 6 root 8 over 8. Now, again, some people would say, wasn't root 8 times root 8 square root of 64? Yes, it is, but the square root of 64 is 8. Here's what I'm going to tell you. The sooner you can understand this, the better off you will be. Anytime you see 2 radicals that are the same multiplied together, for instance, root 12 times root 12, do not multiply the 12s. Root 12 times root 12 is 12. You say, well, 12 times 12, 144. Square root of 144 is 12. That's easy. Well, how about this? What if I gave you root 27 times root 27? You don't know what 27 times 27 is off the top of your head, so you don't want to multiply the two numbers together and see what the square root is. It's a waste of time. Root 27 times root 27 is simply 27, okay? Now, back to my problem, 6 root 8 over 8. This isn't simplified for two reasons. First off, 6 over 8 reduces to 3/4. So I have 3 root 8 over 4. Secondly, square root of 8 is not simplified because the square root of 8, again, like I said earlier, can be broken down into root 4 times root 2, which is 2 root 2. So now I actually have 3 times 2 root 2 over 4. 2 over 4 reduces to 1/2, and I end up with the exact same answer I got on the left side, 3 root 2 over 2. Both options will always work. Whatever you are most comfortable doing is what you should go with. I personally probably would go with the method on the left, but it's your call. Different examples, same rules of division. You cannot have radicals in the denominator, but one rule that really will help us out, there's a rule in algebra that tells us the square root of 27 divided by the square root of 23 is equivalent to the square root of 27/3. I can put those two numbers, the numerator and the denominator, inside of the radical together. Why is that important? Because I know 27 divided by 3 is 9, and the square root of 9 is 3. Done. I don't have to do anything. Nothing else. However, if you didn't realize that, and you wanted to do this problem the long way, you certainly could. You could multiply by root 3 over root 3, and you can get 27 times 3, root 81, divided by root 3 times root 3 is, of course, 3, which gives me the square root of 81, 9, divided by 3, which is the same answer, 3. Either way, you get our final answer, simplified, is 3. Next problem. Again, multiple ways we can do this. Right off the bat, though, I see 30 in the numerator and 5 in the denominator. Let's simplify that to 6 over 1. So this problem becomes 6 root 5 over root 2. How do I get rid of the root 2? I'm going to multiply by root 2 over root 2. So in the numerator, I'm going to take my 6, and now to multiply radicals, root 5 times root 2 is going to give us root 10 over root 2 times root 2 is 2. And then the last step, simplify. 6 over 2 reduces to 3 in the numerator, so my final answer is 3 root 10. There really isn't a better option to solve that problem. I would go with that method. I'm going to spend a little bit more time talking about multiplying radicals. In our first example, 5 root 7 times 3 root 7, the whole key to this problem is understanding what parts of the problem we are going to multiply together. And what we do when multiplying, we always take the number in front of the radicals and we are going to multiply those together. So 5 times 3 is 15. Now, after that, we take the two numbers inside the radicals and we multiply those together. So I could call this 15 root 49. 7 times 7 is 49. However, I'm not going to do that because I've said it multiple times. When you have the same number inside the radical, root 7 times root 7, that is simply 7. So this problem is 15 times 7. So we're just going to multiply 15 times 7, which is 105. And that's your final answer, 105. Now, a problem like 4 root 3 squared, you have to understand what 4 root 3 squared even means. That means 4 root 3 times 4 root 3, which means we are going to multiply the 4's together to get 16, and we're going to multiply root 3 times root 3, which is 3, and we get 16 times 3, which is, of course, 48. We are done with that problem as well. I see a ton of mistakes with adding and subtracting with radicals. First and foremost, if you ever tell me square root of 8 plus square root of 8 is equal to the square root of 16, I may punch a hole in the wall. I may even bash my head through the wall. That is absolutely 100% incorrect. That is not ever, nor will it ever be true. You do not, I repeat, you do not simply add the numbers inside radicals together. You cannot do that. And if you're not understanding why that's true, let me tell you why. If I had something like square root of 9 plus square root of 9, and I set that and I said, well, that's just square root of 18. 9 plus 9 is 18. Let's just call it root 18. Here's why it's so far off. The square root of 9 is 3, plus the square root of 9 is 3. 3 plus 3 we know is 6. Guess what? The square root of 18 is nowhere near 6. The square root of 18, if we use some logic, is between the square root of 16 and the square root of 25. The square root of 16 is 4. Square root of 25 is 5. So the square root of 18 is 4 point something. Maybe 4.2, 4.3, somewhere in that neighborhood. Again, 4.2 or 4.3, that is nowhere near 6. So you cannot just simply add the numbers inside. The rule of adding and subtracting, you add and subtract only the numbers in front of the radical. If there is no number there, put a 1 there. So root 8 plus root 8 is 1 root 8 plus 1 root 8. Simply add the 1 plus 1 and we get 2 root 8. That is the correct answer, except for the square root of 8 needs to be simplified into root 4 times root 2, which is 2 root 2, and we get 2 times 2 times root 2, which is 4 root 2. Again, check it out on your calculator. Figure out decimal-wise what root 8 is, add it to root 8, and see if it's the same as 4 root 2. I guarantee it will be. Okay, moving on to the next problem. Another rule tells us that we can only add radicals if they are the exact same number inside. In other words, I cannot add root 2 plus root 3. Root 2 plus root 3 is impossible. We cannot add that together. So what I'm circling in blue is simplified. I can't do anything with it. It's not root 5. It's not some crazy other answer that I've seen in the past. It is simplified. You cannot put radicals together unless they are the exact same. So in my problem below, I can only combine 3 root 5 plus 1 root 5. 3 plus 1 gives me 4 root 5 minus 2 root 3. I can't do anything with 2 root 3, so what I have circled is my final and simplified answer. It's kind of like trying to add x's and y's together. I can't say x plus y is xy or something crazy like that. It's the same thing. Root 3 plus root 5 cannot be added. X plus y is simplified. Root 3 plus root 5 is simplified. Now for this problem, it looks as though we probably, can't do anything here because 8 and 98 are different numbers. We can't just call that root 106. There's nothing we can do here, right? Wrong. Here's why. We need to simplify. Square root of 8, which we've seen a lot of times now, is root 4 times root 2, which is 2 root 2. And the square root of 98 is root 49 times root 2, which is 7 root 2. So here we actually have 2 root 2 plus 7 root 2, which is, of course, equal to 9 root 2 because I add the numbers in front of the radical. One other note. Sometimes I see the mistake where people call this maybe 9 root 4. No. Whatever number is in the square root is what is in our final answer. Root 2, leave it alone. You see in my final answer I have 9 root 2. Root 2 plus root 2 is 2 root 2. That is correct. It is not 2 root 4. You do not take these numbers and add them together. Leave the radical alone. These next few problems I've just called mixed bag problems. I'm going to try to give you a few tricks along the way to help you figure out some of the simplification of radicals a little bit easier and just some different rules and such along the way. Starting with the first problem, square root of 25 x squared. Guys, basically this is root 25 times root x squared, both of which should be very simple to simplify. Square root 25 is 5, square root of x squared is x, therefore simplifying that would be 5x. Now the second problem, there's a nice little trick we can use here. In my opinion, it'd be really silly to multiply 14 times 21. That's going to give me a really big number. There's no reason. Here's what makes it an easy problem. 14 and 21 both have 7 as a multiple, or a factor I should say. Square root of 14 is the square root of 2 times the square root of 7. And the square root of 21 is root 3 times root 7. Now, what I can do is I can multiply my root 2 and my root 3 together to get root 6. And then root 7 times root 7 is simply 7, so my answer is 7 root 6. Big time saver doing the problem that way. Third problem here, 3 times 12. We're just distributing here, fellas. I'm going to multiply root 3 times root 12, which is root 36, plus root 3 times 1 is 1 root 3. And of course, that's equal to 6 plus root 3, because the square root of 36 is, of course, 6. And those are 3 mixed bag problems. More to come. Big difference between these two problems. The square root of 147 plus the square root of 3, again, for about the billionth time, that is not root 150. We have to simplify. The square root of 147 is root 49 times root 3, which is 7 root 3. So this problem actually becomes 7 root 3 plus root 3. Now we can actually add those together because the number inside the radical is the same. So 7 root 3 plus 1 root 3 gives me 8 root 3, and that's my final answer. Now the second example here, we have to treat differently, because notice how in the second problem both numbers are inside the radical. Really, it's assumed to be there, parentheses, around the 147 and the 3. So this is actually the square root of 147 plus 3. We actually do add here. It's the square root of 150. Of course, the square root of 150 is the square root of 25 times the square root of 6. Square root of 25 is 5. Root 6, this answer is 5 root 6. These two numbers, definitely not the same. 5 root 6 and 8 root 3 are totally different numbers. Again, if you understand what the squared sign means, then this isn't that bad of a problem. It's going to take a little bit of time, but it won't be that bad. 2 minus 3 root 7 squared is the same as 2 minus 3 root 7 times 2 minus 3 root 7. Becomes a FOIL problem. We're going to start with first terms, 2 times 2, which is 4. Outer, 2 times a negative 3 root 7 is negative 6 root 7. Inner, negative 3 times 2 is another negative 6 root 7. Notice how I've put like terms together. And then negative 3 root 7 times negative 3 root 7. This one throws people for a loop. Negative times a negative is a positive, of course. 3 root 7 times 3 root 7 is, of course, 9 times 7. That's a times sign, or 63. So when I put all my terms together, my like terms, 4 plus 63 is 67 minus 12 root 7. Why 12 root 7? Negative 6 minus 6 is negative 12. There's my final answer. That is as simplified as it can be. A few more slides to go here. The next slide is called logic. It says put the number 6, 6 root 3, and 12 in order from smallest to largest. And if we use logic, we can say 6 is the same as 6 root 1, because the square root of 1 is 1. 6 times 1 is 6. And then the second number is, of course, 6 root 3. Can't be simplified. We'll leave that alone. And then the next number, 12, this is where you really have to pay attention. 6 root 4 is the same as 12. How did I know that? Because the square root of 4 is 2. 6 times 2 is, in fact, 12. So when I say put the numbers in order, the crazy thing is they are already in order.
because when we change them so that each of them has the 6 in front, we see smallest 1, next smallest 3, biggest 4. That is why these numbers are actually already in order: 6, 6 root 3, and 12. I chose this problem for a reason, because in triangles you will see numbers x, x root 3, and 2x very commonly used. Next up, put the numbers 4 root 3, 12, and 8 root 3 in order from smallest to largest. I'll let you use logic to figure that one out on your own. Take some time with it. See if you can put those numbers in order without, I repeat, without using a calculator. Next up, we have equations involving radicals. When we solve for x, remember what we want to do: get x isolated. Now, when we have radicals in our equations, they're written differently. We're used to something like 2x equals 10, where the 2 is in front of x. We call the 2 a coefficient. With radicals, we actually put the radicals after our variable. And the reason why is because if I put that radical 2 in front of the x, it could be confusing if you're sloppy, because if I just extended that a little bit, you'd say, well, wait a minute, is that root 2 then an x, or is it root 2 times x? We can't tell. So to remedy that, we've simply put the radicals after the variable. But they work the same way. If we had 2x equals 10, we'd divide by 2 to get rid of the 2 and isolate our x variable. It's no different. We are going to divide both sides of our equation by root 2 to isolate our x. Now remember, we cannot have a radical in the denominator, so we're going to multiply by 1 to get 10 root 2 over 2, which is, of course, 10 over 2 reduces to 5 root 2, which is our answer, 5 root 2. And that makes a ton of sense, because when we plug that back in to check if we've done the math correctly, I'm going to rewrite the original equation. X root 2 equals 10. We said x equals 5 root 2. So let's see if 5 root 2 times root 2 does in fact equal 10. Root 2 times root 2 is 2. 2 times 5 is 10. We've done the math correctly. Now, I could do the exact same thing with the second problem. Divide by root 3 on both sides, but I'm going to give you another method just in case you want to use it. X root 3 equals 15. Instead of dividing by root 3, there's actually a little trick here. I could actually multiply both sides by root 3. Again, it's balancing an equation. As long as I do it on both the left and the right side, it's legal to multiply by anything I want. The reason I'm going to multiply by root 3 is because on the left now, root 3 times root 3 is 3x, and that equals 15 root 3, and then I can just simply divide by 3, and I get a final answer of x equals 5 root 3, because 15 divided by 3 is, of course, 5. Here we simply have more practice. This first one's really quite simple. I'm going to divide both sides by root 2, and this works out really well because the root 2's cancel on both sides, and x equals 6. Easy problem. Next problem. Looks a little bit different. I have more radicals involved. X root 2 equals 8 root 6. But again, I can simply divide both sides by root 2 to solve for x. So x is going to equal 8 root 6 over root 2. I'm going to multiply by root 2 over 2. That's going to give me 8 root 12 over 2, which is equal to 4 root 12. But remember, root 12 can be broken down into root 4 times root 3, which is 2 root 3. So I'm going to take that 2 root 3 times 4 to get my final answer of 8 root 3. And I'm done with that problem as well. Alright, the moment we've been waiting for, our last slide. First example, 2x equals 6 root 10. I'm going to do a division on both sides by 2, and this is actually a very simple problem. 6 over 2 is 3. Leave the root 10 alone. My final answer is 3 root 10. Last problem. A little bit more complicated. I have two options. I can either multiply or divide by root 3. Again, I will decide to divide both sides by root 3 to get my x isolated. So now I have 3 root 10 over 2 root 3, and of course I need to multiply by root 3 over root 3, which gives me 3 root 30 over 2 times root 3 times root 3 is 3. So 6 in essence, but I'm not going to change it to 6 because what I noticed is that the 3 in the numerator cancels the 3 in the denominator, and I end up with root 30 over 2. And that concludes our work with radicals. Look over that a few times. Make sure you understand all of these rules so it prevents you from missing problems that you probably shouldn't miss.